this lesson, we are going to learn how to use the periodic table to determine the properties of elements. First of all, we need to realize that all matters in this world is mostly made from all the elements on the periodic table that we discovered so far. Also, one of the most important information we have to realize that all the elements on here, the majority of them are not stable. And that's the reason why all the matter that we see in our daily life, they exist as compound. Because when atoms combine together to make compound, like water for instance, they are stable. And what does it mean by stable? That means they can exist like this in nature without being reactive to another substance. But if they were reactive to another substance like this, if this substance here were to be reactive, they would bond with another atoms to become stable. And that's the natures of all atoms in this universe. We all want to become stable. But in this case, we are going to look at the valence electron and how we can use the valence electron to determine if it is stable or not. Here I have a quick summary of the valence electron. Again, valence electrons are in the outermost shell, and we know that the first one can only hold up 2, and that's the reason why it only has 2 electrons. And then what we have here is we go into the next shell, and each shell represents specific energy level. In this case, there are 2 energy levels, the first one and the second one. And we notice again, we have elements in group 1A has 1 valence electron. Elements in group 2A has 2 valence electron. We see that right there, 2 outermost electron. And we jump to group 3A, all the elements in 3A has 3 valence electron, and 4A, and so on. And that is the group number represent the number of valence electron. But one of the most important information about the number of valence electron and the way our periodic table organized so that all the elements in the same group has the same number of valence electron. That is because elements in the same group also share similar chemical properties. That is, if they are in the same group, 1A, they will be extremely reactive. The same thing with group 7A, they are also extremely reactive. And we have the other elements. They are still reactive, but they are extremely reactive as 1A or 7A. And let me tell you why. And that's all because of this group right there. This group is known as the noble gas. Okay? Well, first of all, this electron right there is supposed to be right there. So ignore that part right there. So the way it works is like this. The only group on the periodic table that is stable or unreactive, okay, is this group right here, 8A. We call this the noble gas, and they are considered as inert or, another word, unreactive. And think of the word "un." The "un" is a prefix for not reactive. That means it doesn't want to react with anything because it's already stable already. And because all the elements in group 8A are stable, that is because they are inert, unreactive, or they are known as the noble gases, we can look at their valence electron to determine the pattern why they are stable. First of all, we have to realize that if we look at the valence electron, notice how the outermost shell are complete. Because helium can only have 2, and the first shell can only have 2, it is complete. And the same thing for neon. The maximum you can have for the second energy level is also 8 valence electron. And we look at argon, the maximum you can have on the outermost shell is 8. So basically, they have a complete energy level. We call that complete or full energy level. So all the space available in the energy level is occupied by electrons. Let's go back to talk about other atoms. First of all, we know that we cannot change the nucleus of an atom because it is all the way inside. And what we can do is that we can change the electrons because electrons are in the outside of an atom. And the way it works is this. Look at this one right here. We know that these elements are not stable. And the only elements are stable are the noble gas. So what we can do is we cannot change the proton, but atoms can easily gain or lose electron. Now within a period, we have period 1, period 2. If we look at within a period, atom can go that direction to become neon, or they can go backward, okay? If they go backward, they lose the outer shell and they've exposed the inner shell. So this, if I look at lithium right here, it will lose a 1 electron and go back to become helium. So it doesn't matter what noble gas it becomes, as long as it has the number of valence electron of noble gas, it will become stable. So you either go that direction or you go this direction. Let's look at this more carefully. If we go in this direction, what are we doing? Notice here we have carbon, right? Has 4. If we go that direction, it becomes 5. We go that direction, it becomes 6. So if I were to be nitrogen right here, it has 5 electrons. How many more electrons does it need? And the answer is this. It would need 1, 2, 3. So that tells you that nitrogen would need 3 more electrons to become neon. But if we look at beryllium in this case, it has 2 valence electrons. So the option is, again, within a period, you either go that direction and gain electron to become that noble gas, or go backward, and this shell will be completely gone. What you have here is going to be the next inner shell will be exposed as the valence electron. So in this case, it has 2 electrons. It can go all the way over here and gain how many more? 1, 2, 3, 4, 5, 6. And we can look at the periodic table right here. See how beryllium right here, right there, it has 2 electrons. 1, 2, 3, 4, 5, 6. So it would need 6 more electrons to become neon. Or the other options again, we can go backward. Beryllium will lose 2 electrons. It will lose 1 here within itself. And then another one in this box right here. So we'll lose 2 electrons. If we lose 2 electrons, that shell will be completely gone. It will become helium. So which one is smaller in terms of steps? Of course, going that way will be minus 2 electrons. So therefore, you will have minus 2 electrons. And when beryllium lose 2 electrons, the better term would be lose, and this one would be gain. In this case, the better option would be losing an electron. Where in nitrogen, if we look at this way before, nitrogen go this way, it would gain 1, 2, 3. Just 3 more to become stable, so it's gain 3 more electrons. If it's going this way, it would have to lose 1, 2, 3, 4, 5 just to become helium, or just to have the valence electrons of helium. So in this case, the option of gain 3 or lose 5 electrons, which one is easier, or which one is smaller in terms of taking steps? Of course, this one is smaller. So that's the reason why, if we look at the periodic table, there is a common pattern. If we look at lithium, of course, it's going to lose its 1 valence electron and become helium. And we can determine that is going to lose electron easily by looking at the comparison of either going that way or this way. Now, what happens when it loses an electron? In this case, electron, remember electrons are negative, so when it loses 1 electron, lithium will have a positive charge. And let's look at beryllium. Beryllium will lose 2 electrons versus gaining 6 more. So therefore, it would lose 2 electrons. And the charge for beryllium, in this case, it becoming ions, would be 2 plus. So all the elements in group 1A would lose 1 electron because it's easy to lose and become the previous noble gas. Just as we look for sodium right here, it has 1 valence electron, and once it loses this electron, it will come back and become that neon. Now, does it really become that neon? No. It just has the number of valence electron of neon. But that sodium ion now is stable because it has the valence electron of neon. So that's how atom becomes stable. It will lose or gain electron to have the same valence electron as any of the noble gas. So let's go back and look right here. Sodium will lose 1 electron. So therefore, it would have a charge of 1 plus. And of course, potassium would do the same thing, lose 1 electron. We have a charge of 1 plus. Let's go over here for boron. Boron, of course, you have the option of losing 3, or you have to gain how many more? 1, 2, 3, 4, 5. Of course, it's going to lose 3. That's a lot smaller steps that we have to take. And once it loses 3 negative, it becomes 3 positive. And then for carbon and all the elements in group 4A, guess what it's going to do? It's in between. You either lose 4 or you gain 4. In most cases, what happens is this. We have a new characteristic called sharing. And we will talk about this group later. The majority of these elements in group 4A, they always go through this sharing process of electron. And we'll talk about that later, okay? Then we have nitrogen. In this case, nitrogen has 5, so it's going to gain how many more to be stable? Or how many more to have 8 valence electron, like neon? Of course, 5 plus 3 gives you 8. Or the other option is to lose all 5 of its valence electrons to have the valence electron of helium. Of course, gaining 3s is a lot smaller steps. So, of course, you're going to gain 3 electrons. Now, when it gains 3, remember, electrons are negative. So of course, it's going to have a charge of 3 minus. That minus, again, represents that we have gained electron. While the positive indicate that we have lost the electron. And the proton now are more, so we have positive proton. Where in this case, we gain electron, we become more negative because electrons are negative. The same thing for oxygen. It has 6. Of course, it's going to gain 2 more to become stable versus losing all 6. So it's going to gain 2 electrons and become 2 minus. And for fluorine, of course, it's going to gain 1 more versus losing all 7. So of course, it's going to gain 1 more electron. So therefore, become F minus or F1 minus. Now, look at the number of sharing electron or losing electron. That number is also important. First of all, we talk about how group 1A is extremely reactive. And the same thing with group 7A. It is extremely reactive. Look, what do they have in common? We have +1 and -1. That is like the number of steps that they need to get to become stable. In this case, for fluorine or all the elements in group 7A, it just needs 1 more electron. So it will be easily become stable. The same thing with it is also easily become the previous noble gas by losing just 1 electron in that shell. So it becomes stable like that. And that's one possible explanation why elements in group 1A and group 7A are extremely unstable. And similarly, elements in group 2A and 6A, they are also very reactive as well. So that's the reason why atoms of different elements will become ions. And for the remainder of the periodic table, I want you to look at the pattern and determine if the element is going to lose electron or it's going to gain electron. And what ions will they become?